What's up, everybody? We are on to our second section in Chapter 6. It's Integral Applications. So we're going to look at several applications that build on the integral techniques that we have learned so far, those that we saw namely in 5.5 and 6.1. So let's get into it. So these applications, they're all business economics related. So here's the list. We're going to do these 5 types of applications. You're going to see a formula for each one of these. So let me just read them off. We're going to talk about probability density functions. Okay. I don't know if any of you guys have taken statistics or if you plan to take statistics in the future. If you do, probability density functions are definitely a topic in stats. What else do we have though? We've got total income for a continuous income stream, future value of continuous income stream. So those two are connected. And then the last two are connected, the consumer's surplus and the producer's surplus. So those are all heavily economics based. Okay. So let's get into it. The probability density functions is up first. Let's see what we got. So here is our formula. So we write this thing with a capital P for probability. We always find the probability of an x value between two other values, which we call C and D. Right? Typically, on the integral, we have the integral from A to B. So we're saying, okay, don't put the A to B because the A to B is might represent like the entire domain. Instead, write C to D, and that kind of indicates we're taking like just a small chunk of the entire domain of f of x. Okay, anyway, whatever these two numbers are, those are your lower and upper bounds. The f of x we refer to as the probability density function. So that's where we get the name here. Okay. In taking this integral, what are we finding? We're actually finding a probability. It says it right here, but let's just be clear. We're finding the probability that our variable falls between two numbers. So what are the chances that x falls between C and D? Turns out that's exactly what this integral is going to do for us. Let's see this in a problem, in an example, make a little bit more sense of it. Okay. Here we go. We also want to see how this thing is presented, because the way they write the f of x is a little funky, the way they typically present these. All right, so what do we got here? Our example says the daily use of water in hundreds of gallons per household is given by this function right here. So imagine they might be talking about like a particular city or country even. Okay, but think of all the households, so they all use different amounts of water. So the probability density function is this. And what's going on here? So we've got a piecewise function. We haven't seen those in a while. The first piece is 0.25e raised to the negative 0.1x. We use that if x is greater than or equal to 0. Okay, and this function equals 0 otherwise. Like, well, what does otherwise even mean? Yeah, I know it's kind of strange the way they present it, right? Other than x greater than or equal to 0. Well, wouldn't that mean x is less than 0? Well, yeah. In this case, yes. Here's the thing: this, where it's equal to 0, right? Obviously, x represents the daily use of water, how much water is being used in a given household. No one's going to use a negative amount of water, right? So you might think like, why is this even here? I agree. That's just the way they present these things. That's how it goes with probability density functions. Okay. So really what we're focusing on is this upper part where, okay, it could equal 0. All right, if a household used 0 water for a given day, but probably we're going to have some positive number, some positive gallons of water, right? Okay. If you were to look at this graph if we kind of wanted to get a little bit deeper in this problem, this graph would begin at this number here. I don't know if you can see my drawing too very well. 0.25. Now this is hundreds of gallons, right? So that's actually 25 gallons per day. And then it's going to drop off. Okay, like so. So the e to the negative means it's like decaying, right? So what does that mean? So this represents probabilities. So the probability that, our household is like out here. Actually, a second ago, I got to correct myself. I said 0.25 gallons. My mistake. This represents the probability, and this represents X. So maybe, like, hey, they consume like, where's 1? That's like 100 gallons. 2, 200 gallons, right? This would tell you the probability. So the chances that they use 0 gallons, right? So smaller amounts of gallons have a higher probability, and as the hundreds of gallons increases, the probability is dropping off. So there's very few homes that use like hundreds and hundreds of gallons. Most homes are down kind of at this beginning end, like in the 100 to 200 kind of gallon range. Those are higher probabilities. Okay, just trying to give you an idea of what's happening here, and trying not to confuse as I do that. Okay, so let's do this problem. What are we actually asking? All right, so we're gonna have two different things we're gonna investigate here. Part A says, find the probability that a randomly chosen household will use between 100 and 300 gallons per day. Right, so imagine, this graph, like 300's out here. We're going to end up finding this area between 100 and 300. And that area represents a probability. Okay, so let's go for it. We're going to say, all right, using our f of x, and remember, we only need the positive part. We're talking about positive x values. So we're just going to take that 0.25 e to the negative 0.1x. Okay. The probability that x falls between 1 and 3. Why 1 and 3? Okay, remember, x is in hundreds. So that's key here. So between 100 and 300 means we're going to integrate from 1 to 3. And then we got our function 0.25 e to the negative 0.1x dx. If we can figure out that integral, then that's going to be our probability. Okay, well, let's investigate. Looking at this probability, you might say, hey, 0.25 is in front. We could move that to the outside. Yes, you could. Looking at the rest of it, e to the negative 0.1x. You could do a u substitution here. We've done these quite a bit already. There's a reason why I'm writing it on the yellow, right? We could take u to equal the negative 0.1x. We could then find out how du is connected to dx, do the substitution. Okay, because we've done these types of u substitutions quite a bit, I think we're ready, some of us, ready to go to the next level and get to our antiderivative a little bit quicker without using the u substitution. Here's how it would work. Let's just do it. Right, the 0.25 stays. Our antiderivative of the e just repeats, right? But because it's negative 0.1x, we're going to have to divide by negative 0.1. Why? Well, if we went through the u sub, right, it would be clear, like we would have to divide that negative 0.1 over onto the du side. Another way to think about it, though, is, hey, if I was to take this derivative, it would be e to the negative 0.1x, but then I would multiply by that derivative, negative 0.1, but I don't see that here, so I need to divide by negative 0.1 in order to cancel that out. Okay, hopefully you followed that. If that's a little much, if this doesn't quite make sense, hey, go ahead and do the u substitution. Although I think a lot of us, or at least I'm going to push you, we can go and do this a little bit quicker now since we've been using use substitutions for several sections at this point. Okay, so there we go. Let's go ahead and clean this part up. 0.25 divided by negative 0.1 turns out to be negative 2.5. E to the negative 0.1x evaluated from 1 to 3. And we'll go ahead and plug these numbers in. Notice I'm just going to keep that negative 2.5 out front and say, all right, let's plug in the 3, subtract, let's plug in the 1. It's a little bit simpler just to keep this out front. And at this point, we've done it, but we'd really like to get a decimal approximation here. We're talking about a probability. So go ahead and throw that into a calculator, and you should get this. I rounded that to 3 places, 0.410. What does that mean, 0.410? This is a probability. You could interpret that as a percentage, 41.0%. That would be fine. So in other words, there's a 0.41 probability, or you might say a 41% chance that a randomly chosen household will use somewhere between 100 and 300 gallons per day, at least given this probability density function that we have. Okay, that's the idea. Kind of cool, kind of cool. All right, I have a part B though here. Part B says, let's get rid of that U. Find D so that the probability is 0.70 or less. Now that's interesting. Okay, remember the D, that's the upper limit in the integral. So they're not going to tell us the D. We got to figure it out. What D so that the probability is 0.70 or less? Okay, let's go back just to our original formula. Okay, when we say 0.70 or less, that means we're going to go from 0 to D. Okay, what's the D? What would the upper limit be? We need a 0 because it's or less, so anything less than that. So less all the way down to 0. Okay, so, and then we got our same f of x there, dx. How do we figure out what D is? I mean, what are we going to do with that? Okay, because we know that the probability is going to be 0.70. So when we integrate from 0 to D, we know our result is going to be that 0.70, or you might call it 70%. Well, this is nice. It's the same f of x, so we get the same antiderivative, right? And I just went ahead and did the simplified version when we divide by negative 0.1. So negative 2.5 e to the negative 0.1x evaluated from 0 to D. And here's how it's going to happen. We're going to plug in D, subtract, plug in 0. We know what it's equal to. We'll be able to solve for D. Right, 0.7 equals negative 2.5 e to the negative 0.1 D minus, and when we plug in the 0, well, e to the 0 is 1. Can we solve for D? Yes, we can. Let's do it. I'm going to divide by negative 2.5, negative 0.28. Here, I'm going to add the 1. Happens to be 0.72. Okay. We're going to take the natural log of both sides to cancel this e. Natural log 0.72 equals negative 0.1 d. We're going to divide by negative 0.1, and my paper came to the bottom edge of my paper, so we'll just wrap it up here. Natural log 0.72 divided by negative 0.1, right? Put that in a calculator, you'll get 3.285. That's the D. What does that really mean, though? I mean, that answers the question, but how does that connect to like the gallons and stuff? So remember, that's in hundreds of gallons. So we're talking about 328.5 gallons per day. So we're saying the cutoff to mark 70%, like the lowest 70% of the households would use somewhere between 0 and 328.5 gallons per day. 70% of the households between 0 and this means 30% of the households are above that number. I don't really have a good idea of how much water that is compared to a household, but it seems like a lot to me. Okay, very nice. Let's stop this first video here. Coming up, we got more applications.